there everyone, my name is Glory Valentine. I'm a PhD candidate, the Department of Metallurgy and Structural Integrity from the Center for Research in Advanced Material Science, CMA. I thank the organizers of the 16th CSM conference. As part of my research work, I will be talking on the role of ex-situ thermal treatment on the oxidation state of bismuth manganese oxide tin film. I would like to start with a question. Why are the oxidation states of bismuth manganese oxide tin film important? These contribute to its physical properties, which are the distinguished characteristics that describes the materials. It influences magnetic property, provide important information for the application of this material. Such applications include actuators, magneto-electric-based devices, and non-volatile data storage devices, among other possibilities. In this work, two samples marked as bismuth manganese oxide BTT, which signify ex-situ thermal treatment, and bismuth manganese oxide ATT, which signify ex-situ thermal treatment. So I will be using this abbreviation for before ex-situ thermal treatment and this for after ex-situ thermal treatment. These were deposited on platinum substrate using the radio frequency magnetron sputtering technique. The volatility of bismuth in the target was compensated during ex-situ thermal treatment. The structural and morphological analyses were carried out to investigate the role of ex-situ thermal treatment on the oxidation state of bismuth manganese oxide tin film. The main objective was to investigate the role of ex-situ thermal treatment on the oxidation state of bismuth manganese oxide, to grow bismuth manganese on platinum substrates by radio frequency magnetron sputtering, and finally, to study the structure and morphology of bismuth manganese oxide tin film. These were the experimental parameters used. Here, in material characterization, we make use of the X-ray diffraction, energy dispersive X-ray spectroscopy, high-resolution transmission electron microscopy, and X-ray photoelectron spectroscopy. This is one of the experimental techniques which I really like, the radio frequency magnetron sputtering, and here we have the high-resolution transmission electron microscopy, which was used for the characterization. Results and discussion. In figure 3a, we have the low magnification 10 microfight, and here is the thickness incorporated for the visualization of the element bismuth manganese oxide film on platinum substrate. It was a buffered platinum substrate which it has the titanium here and the silicon oxide. From observation, there was no void or crack in the material. See here, we have the HR10 results, which clearly shows evidence of randomly oriented nanocrystalline. This yellow region is the single crystal, which is represented in D. In accordance with the interplanar distance illustrated in 3e, where the interatomic profile distances with the interplanar distance equals minus 113, which equals to 2.80 Armstrong. On the other hand, the figure 3f shows the fast Fourier transform pattern of the region marked with a red frame, which indicate the presence of the Gibbs rings that clearly shows the plane minus 113. This indexing was done according to the XRD PDF card, which is the monoclinic C2 space group number 5. In summary, the results have provided a clear indication of the nanoscale bismuth manganese oxide tin film. To find the valence state of manganese and also oxygen bonding characteristic of bismuth manganese oxide thin film. X-ray photoelectron spectroscopy was conducted. Here in 4A, the oxygen spectra of the two samples is resolved into three peaks. We have one at 229.7, then we have another at 530.6 electron volts, and the last we have it here to be the 3 to 1.1 electron volts. In addition, an overlap is being observed here in the sample before annealing at 533.7 electron volts, which can be attributed to the uncoordinated oxygen. Also, the peak here is more intense than the after ex-situ thermal treatment. This suggests the presence of oxygen defect in the nano-size bismuth manganese oxide crystalline. In figure 4B, we have the Mn spectra, which shows the features of the 3 plus. Here we have the 4 plus oxidation state. In after ex-situ thermal treatment, we only have the 3 plus. But here we have both the 3 plus and the 4 plus, indicating that the ex-situ thermal treatment induces the sample to a stoichiometric structure observed from the binding energies MnF at 653.7 and also 641.7. In conclusion, bismuth manganese oxide thin film were obtained using radiofrequency magnetron sputtering method. The crystal structure and the microstructure were investigated via X-ray diffraction, scanning electron microscopy, high-resolution transmission electron microscopy, X-ray photoelectron spectroscopy. The findings provide a visible growth of high-quality thin film of bismuth manganese oxide, hence reveal the simultaneous presence of the Mn3 plus and the Mn4 plus ion in bismuth manganese oxide, the one without ex-situ thermal treatment, and Mn3 plus in the sample with ex-situ thermal treatment. Thank you for your time. The authors acknowledge the support of partnerships and thank the members of staff at the Center for Research in Advanced Materials Science, CNAP. I will be glad to answer all your questions.